In this lab, we're going to be using an air track to talk about collisions. So we're going to examine the conservation of momentum, and then we're going to verify that momentum is conserved in elastic and inelastic collisions. If you remember from class, we talked about how momentum is conserved if there's no external forces. So in this case, your system is going to consist of two carts, one cart over here, and they're going to come into each other, and in the middle, they're going to collide. And then, depending what's on, if you're in an elastic or inelastic collision, little tongue-tied, they will bounce back, or they will form one big super blob and go some direction. So remember that we talked about momentum. If we call this cart m1, this cart m2, momentum, P is just equal to mass times velocity, and you add up all of your mass times velocity. Remember that this little sign right here means it is a vector. So you're going to have to add these components. So to study momentum, we are going to be using an air track. And that is what this thing is right here. It is an air track. It looks like someone wrapped an air hockey table around a pole. And that's exactly what it does. It provides a nearly frictionless surface for these carts. Very important. Do not put the carts on the track unless the track is on, unless there is air flowing through it. Otherwise it can scratch. Second part that you need to know, these little gate-looking things are photo gates. They talk to the computer and record your data. And I guess the fourth thing, I don't remember where we are right now. You have to level this track. And the way you do it is with these little screws. You raise and lower them so that your track is level. So please take very good care to level your track. Now let's talk about what you do with this. But first, we're going to do air analysis a little bit differently. So your cart is going to go down this track like so. And it's going to pass from one photo gate to another. But the problem is you don't know how fast it's going. So what you're going to do, there are a couple of things that can kind of impinge on this. It's nearly frictionless, but you're going to calculate error from friction. And you're going to do this by taking multiple runs at various speeds. So what this looks like, if we saw that video, you run it through, it's going, this photo gate, the initial one, takes its initial speed, this measures its final speed, and you look at the difference. And the loss of that is going to be your loss due to friction. So another area where momentum can go to places that are unaccounted for are in the collision with this rubber band itself. Energy can turn into heat because you'll hear this, it'll compress, and it's not 100% effective at transferring momentum. Not 100% inelastic, one would say. So what you're going to do, just like before, you're going to make a table for rubber band error. And you're going to collide the cart with the rubber band, measure the speed in and out for various speeds, and again, get your percent loss. Okay, so what you do with error, let's say that your relative velocity, and again, always look at relative velocity, the velocity of the two carts added together, is 1 meter. Actually, when we look at our data, we find out that 1 meter is horrible, so scratch that collision. Let's make your relative velocity, and that's what you do. What you'll see is your friction percent error is going to go up as you go slower, while your rubber band percent error is going to go down as you go slower. So you want to find a maximum value, and it looks like the sweet spot in here is going to be somewhere around 0.5. So let's say your relative velocity is 0.6 meters per second. This is very slow. So then what you would do, well, that's closest to here, so you take 2% from friction, you take 4%, and you get your total error on that run when you're comparing your conservation momentum, or your conservation momentum values, is going to be 2% plus 4%, which equals 6%. So if your values are different by less than 6%, your momentum in, so P1 and P2, if they are less than 6% difference, that means it's consistent, and that's how we're going to do error in this lab. So you build your two tables and compare the value for your relative velocity. So you're going to do multiple trials at each run to make sure you get a good one. This is set up for the elastic collision, and you can tell because one of these bumpers has a rubber band on it, which means they're going to bounce. So they'll hit, you do multiple trials, and then you're going to repeat, but one hanger, only one hanger, has this mass on each side. So you repeat with extra mass. Something to note, you need to get the mass of this, you need the mass of each cart, you also need the mass of these added to each other. Now each mass, or each thing that you add onto the end of this cart, has a mass of 5 grams. So just add 5 grams twice, so 10 grams total. Also, to keep things balanced, make sure that if you add something on this side, you also have something on this side. Otherwise, your cart's going to tilt, and you don't want it to do that. So this is for verifying elastic collisions. Next, we're going to look at inelastic collisions. Point of safety. This is sharp, so don't touch it or put your hand in there, or your partner's hand. So go very, very slowly when you collide. The second part, this is just a wax. It's got a wax little hole in there. So these will slide and they'll hit together and they'll stick. So this is inelastic collisions. So before it was elastic, this is inelastic. So when you're running your inelastic collision, it looks like this. This is the one with the extra mass. Key point, it moves really slow. So when you're doing your extra mass, make sure they collide near a gate. The other thing to note is stop the timer when one goes through. So stop after one cart goes through. Those are pretty important tips. So collide next to a gate when you have the extra mass. When you don't have the extra mass, it doesn't really matter. But when you do have the extra mass, definitely collide near a gate. And also, stop it after one cart goes through. So let's talk about how we're going to collect all this data. You are using graphical analysis, so it's all on computer. This photo gate distance, this is the cart length. It has an infrared sensor, and it knows how wide the cart is. So the beam gets blocked, it starts a timer. Beam gets unblocked, ends the timer, and it calculates these velocities right here. Gate 2, gate 1. Now you will notice there are no negatives, so you have to assign positive and negative values, otherwise your momentum won't come out. Now again, this is because momentum is a vector, plus and minus values. So in a collision, going in, let's assign going in this way was positive, which means this one's negative, and then this one's negative coming out, and this one's positive. That's because your initial setup has two things running at each other, and then the final setup has the same two things, but now they're going the other way. And this just assumed that this way, well actually, given this thing real quick, sorry, that assumes that this was my plus x. It doesn't really matter. You just have to assign and know that if one goes in positive, it comes out negative. If it goes in negative, it comes out positive. A couple major points: collide the carts very slowly, as silently as possible. If you can hear it, it is too fast. So they are quiet. Very quiet. Alright, if you hit, you can hear it, you're losing energy as sound. It's not what we want to do. Second part, and I see this every year, make sure you use the relative velocity to calculate your error. So if you're colliding and you have one going at 3.5, and by the way, 3.5 is incredibly fast, and your other one is 3.5, your relative velocity goes to 7 meters per second, which is too fast because it's not quiet, as we mentioned. So to wrap this up, examine momentum conservation. You're going to compare P initial and P final. And then hopefully your percent difference, this is actually this is different than any other one we can use. Hopefully your percent difference is less than your percent uncertainty from the tables. And, sorry, I write like a kindergartner on this thing. So your percent difference is less than your percent uncertainty. You're calculating the coefficient of restitution, and that is just how elastic your collision is. And remember, this is relative velocity out or before, well, sorry, out is after, and relative velocity in. Absolute value. If it is 1, it is perfectly elastic. The final thing to do, make sure you have multiple runs. And that's the lab.